All right, the last point that we got to last time was these introductions of the KPs and the KXs over on the right. And the big advantage of that was that previously we had only known how to do K0, K1, K2, all of which were functions of temperature. And now with the addition of KX and or K, well, KX or KP, we have a function of potentially pressure, if it's a gas phase, and the extent of reaction. There's several different ways you could write that. It could be pressure and moles, pressure and extent of reaction, or pressure and conversion, as we had been using every once in a while. We will see another version next week, but it's consistent with all of those, right? I can write these reactions in terms of moles or extent of reaction or conversion or whatever I want. They're all kind of interchangeable. They can go back and forth. And so that was our link between the two of those. I wanted to work a little bit on two parts of this. One is to talk a little bit about KP, and then talk a little bit about this function of temperature. That'll probably take us about 20 minutes or so. And then after that, we've got the in-class example that I had mentioned last night that can get you some bonus points on the first homework. Somebody has informed me that there might have been a mistake on the K that I gave in the last example yesterday. I will double check that and add a comment. I used to be able to annotate YouTube stuff, but they took annotations away off of YouTube, so it'll just show up in either the comments or the description on TritonEd. There'll be any notes that I need to make there. So if I correct any of that, you'll see it on both TritonEd and YouTube. Let's work on KP first, since that was the first thing that that was the most recent thing that we worked on. Yesterday, we needed KP in that example. And I had some pretty good questions after the class about where all of the exponents came from, how we went from partial pressures to mole fractions, and why that extra total pressure was floating around afterwards. So we will briefly describe that. Remember, KP is defined as the product of all of the partial pressures raised to their stoichiometric coefficients. We can write that in a more common way, the way that you will typically see it written. If we substitute for any partial pressure I, is the mole fraction of that species times the total pressure. Keep in mind that this is always bar. If you ever use a pressure in any one of these, always set it to bar before you go any further. The reason for that is because there's a hidden P circle sitting in there. We never write the P circle because it's always got a numerical value of 1, but it's there, and it's forcing us to use these units. So if we make that substitution, the result on the other side looks something like this. I'm going to do it for that classic A plus B goes to C plus D kind of thing. What we have then is the mole fraction C. I'm going to have to move that up a little bit. We need a little more room. Mole fraction C raised to the C power, D raised to the D power, A raised to the A, and B to the B. All of that times pressure raised to C, no, not copy, pressure raised to D, pressure raised to A, and pressure raised to B. So I did one extra step there, right? I isolated all the mole fractions on one side and all of the total pressures on the other side. One way that you will see this commonly written is a K sub Y. So now we're up to who knows how many Ks that we have right now. Because that K sub Y kind of looks like the same Ks that we've seen before. So K sub Y is the product of all the mole fractions of Yi raised to the stoichiometric power, or stoichiometric coefficient. But then it's multiplied by something else, right? It's multiplied by that total pressure. It's the same total pressure everywhere, so we can factor that total pressure out. And the exponent there becomes the sum of all of the stoichiometric coefficients. That was where that other P came from when we were working that example yesterday. Usually you'll see that P raised to the sum of the stoichiometric coefficients over on the other side, because remember, all of this is equal to K. And so often you will find that P raised to the sum of the stoichiometric coefficients put over on the other side. there's no reason to do that other than what we're about to discuss, just because it reveals the dependence on pressure. So that was where those pressure terms came from. That's a pretty, almost any time you do a gas phase reaction, you're going to have to do that. As you do it more and more, you'll get a little bit more comfortable with it, and maybe you'll just start skipping over to the last part here. But until you're pretty comfortable with it, don't skip steps. Just write out that middle section, and that way you'll avoid making any mistakes. The reason that it's sometimes moved over to the other side, the K parameter, is if we look at Ky, generally that can be interpreted as the concentration of products over the concentration of reactants. Generally, right? It's not exactly equal to the product of the concentrations. They're raised to various powers. But if you do like a hand-waving argument, if you want to know generally, am I favoring products or am I favoring reactants, that's the pattern that we've got. All of the products end up on the top and all of the reactants end up on the bottom. This is therefore also kind of like saying the conversion F. So F is our conversion. Right? Higher conversion means we are favoring products, which is usually accompanied by a higher Ky or Kx in that matter, for that matter. And so the opposite side of this then looks like if we move this P over to here, that Ky then is equal to K divided by P raised to the sum of the stoichiometric coefficients. And just to be entirely clear about which K's we're talking about there, because we have a lot, that's like saying K0, K1, K2 divided by P raised to the sum of the stoichiometric coefficients. This is usually the part that we're interested in, this part here in the center. Right, that's the relationship that's of interest to us most of the time, which is if I change pressure, what happens to the relative concentration of products versus reactants? Or in shorthand, if I change pressure, what happens to conversion? Right, does it go up or does it go down? It depends. Based on the sum of the stoichiometric coefficients there. Sometimes for some reactions, pressure will be good for you if you increase pressure. Other times it will be bad if you increase pressure. Other times it will have no effect at all. And so what we're going to look at is the variations that we can have based on this particular term. Everything comes down to whether or not this term is positive, negative, or zero. The effect of that term being positive, negative, or zero is indicated by the stuff in the box there. Yeah?
What is the sign before the conversion?
What's the what?
What's the sign before conversion?
The sign of conversion?
The sign before conversion.
Oh, the symbol? Approximately. Right, we're using more like word equations than actual numeric equations here. So the ratio of products over reactants is kind of like talking about conversion. Because if I increase the amount of products I have, that means I also must have increased my conversion. So the squiggle there, the tilde, looks like. So 3 quick cases for this. Case 1 is if the sum of the stoichiometric coefficients is less than 0. If we do that, we'll just assume every time that you want to raise pressure. So if you have a higher P, or if you raise pressure somehow, the result is that you end up having a smaller value of P raised to the sum of the stoichiometric coefficients. Right? That's like raising pressure to a negative exponent, which means it's like 1 over pressure raised to that exponent. And so the result is that P raised to the sum of the stoichiometric coefficients goes down. And as a result, Ky goes up. If Ky goes up, that means you're favoring products, or in general, you are increasing conversion. So for this particular case, this favors products. The other cases are pretty similar. Case 2 is the easiest one, which is that the sum of the stoichiometric coefficients is equal to 0. That one's easy. Pressure has no effect. In that particular case, any pressure that you have, whether it gets high or whether it gets low, always ends up being raised to a 0, and so it doesn't have any effect. It doesn't react. Well, it does react. It has no effect for pressure. And then you can probably guess what case 3 is. Case 3 is if that sum of the stoichiometric, what was case 1? Less than 0? Greater than 0 is case 3. And so again, here, if you try the same pattern, if you increase pressure, the result is that you'll have a larger term on the right-hand side of that equation that we had talked about a minute ago. So if the sum of the stoichiometric coefficients is positive, greater than 0, when you raise p to a positive number, that number gets even bigger, and therefore the ky value gets even smaller. And so this one would favor the reactants. Generally, if you calculate conversions for each one of these, right, if you take base case A was at some pressure and then case B was at some new pressure, usually this one means that the conversion goes down, and this one means that the conversion goes up. So if the sum of the stoichiometric coefficients is less than 0, like in case 1, and you increase the pressure, that will generally force your conversion to go up as well. It's just the opposite for case 3. If you increase the pressure and the sum of the stoichiometric coefficients is greater than 0, generally your conversion will go down. Right, we're talking about general trends there, like if I have to improve the behavior of my reactor, should I increase or decrease the pressure? This will tell you what that is. If you want a quantitative estimate of what that effect is of changing pressure, you just have to do all the math. This is not giving you a quantitative result, but it should give you a good rule of thumb to check your answers, right? You can at least verify that your math was correct using trends like what we've got here. Yeah. A case 2, a good example of a case 2 reaction could be anything like A goes to B. That is pretty common of what's called an isomerization reaction. So it's the same overall molecular structure. You might just move one of the groups from one side to another.
Similar to like a cis and trans.
Yep, exactly. Cis and trans is an excellent example. If you think of like long chain hydrocarbons that have little branches, you could move one of those CH3s from one branch to another. That would be the same thing, where you haven't done anything in terms of adding or removing elements like atoms or molecules. You've just reshuffled the ones that are already there. That's usually what's happening in a case 2. That also tends to be a nice one for like exam type problems, because then you don't have to worry about pressure, and it tends to make those integrals a little bit easier. You haven't done any integrals yet, but next week we'll see integrals. Good question. Any other questions? While I wait for questions, I like to underline things. Nada? Okay. So pressure is generally captured in that Kp term. By the way, if you have a liquid, pressure has no effect. We assume things are incompressible, so that's why pressure never shows up anywhere in any of our terms. The other effect that we're worried about is temperature. What does temperature do in terms of conversion or favoring products versus reactants? We will look at temperature based on our original K. Actually, let me create a header here. Temperature effects. We can learn 3 good things from temperature. All of the temperature effects we are primarily worried about are the ones that have to do with K being equal to K0, K1, K2. Right, as I summarized at the beginning of the lecture, all the big temperature effects are coming in through there. There might be mild temperature effects over on the right-hand side, but they are because of the KPs and KY terms. If you include things like phis and gammas and that, they're usually swamped by the behavior of this particular one, so we get away with just looking at this particular one. To simplify our discussion, we're going to assume delta H is constant. If we assume that delta H is constant, then that means K2 is exactly equal to 1. And so we end up with something like K is approximated by K0, K1. That's our shortcut version, right? Whenever enthalpy of reaction is constant, we can get away with a shortcut approximation. It's just going to make our math a little bit easier. Again, if most of the temperature variation is from K0, K1, and K2, within that group, the vast majority of that temperature variation is coming from the first two. This correction, as I had mentioned a few times last time, is pretty small. So just to make our lives easier, we're going to ignore that one as well. You can certainly include it if you want. If we take the derivative of those with respect to temperature, and notice I left a big gap there. Again, the math gets a little bit easier if you don't take the derivative of K with respect to temperature, but you take the derivative of the natural log of K. Because remember, K0 and K1 are both raised to exponents, right? E raised to something. If you take the natural log and then take a derivative, that becomes a little bit easier. What you end up with is the derivative of the natural log of K0 with respect to t and natural log K1 with respect to t. The first one is easy. That one goes away, right? It was always at a single temperature. The actual temperature we are running our reactor at never showed up inside K0. That was always for reference temperature. So this particular term goes away, and all we're left with is the second one. This is saying you need to take the partial derivative, or sorry, the total derivative with respect to temperature of delta H over RT ref times 1 minus T ref over T. If you do that math, what you end up with is dlnk, which I think you can probably do that math without too much. It'll probably take you a couple of lines, but it's not awful, right? There's only one temperature that shows up in there, so it's not terrible. Is equal to delta H divided by RT squared. You've probably seen that form before. Sometimes the discussion of equilibrium starts with this particular expression, and then you develop variations of that expression to be used for different reasons. Whoa. I don't know why that did that. What we're interested in is what's the effect of temperature, right? This is telling us what the effect of temperature is, because what this is describing is essentially the slope of K, or the slope of ln of K, when you plot it on a plot versus temperature. And the entire variation in slope, wherever that slope variation comes from, is all dictated by the sign of delta H. The t, you might initially think, well, yeah, it depends on temperature too, because there's a t squared in the bottom. That's only describing the shape of whether or not it's describing the shape of the curve, not whether or not that curve is going up or going down. It might be bent a little bit, as it usually is, but in general, not in general, all of the behavior in terms of either going up or down is captured by that delta H. So just as with pressure impacting our conversion based on the sign of the sum of the stoichiometric coefficients, the temperature is dictated by the sign of the enthalpy of reaction, and that can be either positive or negative. I've never seen an example where enthalpy of reaction is 0, so we don't approach that case. If it were 0, then temperature would have no effect whatsoever. So in the case of delta H, that's a little cramp, being greater than 0. Anybody remember that one? It's called a what kind of reaction? Endo. That's the one that doesn't happen all that commonly. But if delta H is positive, that says if I plot the natural log of K versus temperature, it's generally going to go up. Which means if I increase T, a higher T ends up with a higher K, and a higher K means a larger conversion. In other words, that favors the products. Equivalent conclusions there. Either the conversion went up or the products were favored. What does that mean? If you have an endothermic reaction and you want to get more product, heat the thing up. You'll get more product. Yeah.
So for delta H here, doesn't it also depend on nu?
You mean that, so, yeah, delta H is equal to this?
Yeah.
Mm-hmm.
Have a similar cases
Not necessarily, because this particular term, if you look those up, the enthalpies of formation can be either greater than 0, equal to 0, or less than 0. And so any trends that you might find in the stoichiometric coefficients aren't necessarily relevant until you combine them with any trends in the enthalpy of formation. And so the net effect is the enthalpy of reaction is the thing that's dictating whether this is good or bad to increase temperature. So yeah, the stoichiometric coefficients are still there, but it's not helpful to look at just those because the enthalpies of formation are also important. So you have to consider them together. You can probably guess what the other case is. The other case is if delta H is negative. These tend to be a little bit more common. The exothermic reactions. What that previous expression was saying is if I plot ln of K versus T, now the slope is negative. And so if I increase T, that will generally lower K. And as a result, I have a lower conversion. Or another way to write that is that this favors reactants. And those should be consistent with anything that you would have seen in chemistry. Our world is the same as the one that the chemists work in, so that's good that our answers agree with theirs. There's one other nice thing that equation can tell us, completely unrelated to whether or not something changes in a favorable way or an unfavorable way with temperature. If we look at this particular expression, the only requirement that we had for that particular expression was that delta H was constant. If delta H is constant, then this is true. Actually, rigorously, that is true because K2 will be exactly equal to 1. And so that expression relating ln of K to temperature is exactly true if delta H is constant. As a result, we can just integrate both sides of that. If we integrate both sides of that from any arbitrary K and initial temperature to any other K and any other temperature, so if you separate that, it's a nice separable one. Right? If I separate that and I just set the bounds completely arbitrarily, so I can go from any temperature T1, which can correspond to any K1, as if somebody gives me that K1 at a particular T1, I can use it, to any other T2, and I want to calculate the corresponding K2. what I end up with is the natural log of K2 over K1 is equal to delta H over RT1 times 1 minus T1 over T2. This looks very similar, or it should look very similar. This is like saying essentially K is equal to K0, K1. Right, that should look kind of similar to what we had before, except now instead of, you can see why now it's confusing because there's two K1s in there. But that's why I put that as a different color. If I know any K, it doesn't matter what temperature that K is at. If I know that K at a particular temperature, and I know delta H is constant, then I can use this expression to scale that K. That's mostly useful in a homework situation where I can give you a K at a particular temperature and tell you that delta H is constant, and then you can scale it that way. The advantage of that is only that you don't have to calculate the exponential of delta G ref over RT ref. You don't have to do that anymore, right? If I just flat out give you a K, you can always calculate the other one using this equation. So for example, what would that look like if I actually gave you that information? I could say, given K is equal to 6 at, who's got a favorite temperature? Yell out your favorite temperature. 16? Okay, 16. What? 298 point, no, you can't do the reference temperature. I heard 16 a minute ago. Right, somebody just gives you a random K at some temperature, whatever it is, and they also tell you that delta H is something, right? So maybe minus 40 kilojoules per mole. And importantly, that they tell you that this delta H is constant. That's kind of a shortcut way of me letting you adjust K for any temperature to a pretty good approximation. We've lost the K2 approximation, but that's not bad. If I do something like that, what I end up with is that K2, or I should say K of any temperature, is equal to the K that I just gave you times the exponential of delta H over RT 1 times 1 minus T1 over T. Right, so you plug in, instead of K, you plug in 6. So the 6 goes here. The 16 degrees C goes here for T1. Remember, you always have to convert it to Kelvin or absolute temperature scales. So the T1 goes there, and then the delta H goes out here. So it's just a shortcut way of us being able to give you a K instead of having to give you all of the Gibbs energies of formation, all of the enthalpies of formation, and then asking you to use the full K0, K1. We can just give you a K at a temperature, and then you can use this expression to scale it. Anybody keeping tabs on how many Ks we have now? I think it's like 14.
What's the T2?
T2.
Like 1 minus T1 over T2?
Oh, that's the other temperature. So if you want to scale it, in this example, from, say, 16C up to like 40C, then 40 becomes T2.
But where did you get the 40 number if it's happening at 16C?
I'm saying if I give you this example and then I ask you, for example, what's K at 40 degrees C? Or the reactor is run at 40 degrees C, or something like that.
And you don't want to recalculate the shortcut Van Hoff again?
Right. Well, this is essentially the shortcut Van Hoff. What you don't have to recalculate is all the delta G's and delta H's, because I've just said it's constant and here's a K. The big advantage to that is not so much here's a K, run a batch reactor isothermally at a different temperature. The big advantage is when the temperature changes in the reactor itself. This is a little bit more user-friendly than having to go through that entire process all over again. Yeah?
When you T1 or T2, should we keep it in Celsius or Kelvin?
Always Kelvin. So just like anytime you ever see bar, anytime you ever see temperature, put it in Kelvin. Your life will be easier. Yeah?
When can we assume voltage is constant?
If you don't have information about CP, or you have to do the calculation a lot. There's not a great rule of thumb. The other kind of rule of thumb is small temperature changes. So if you're maybe 50 degrees Celsius or less from one temperature to another, it's usually pretty small. If you can calculate the full Van 't Hoff equation, do it, because that's the only way that we know whether or not it's important or not. Even for very small temperature differences, depending on the reaction that you have, that temperature can be really important. And that temperature dependence is less so here, more so in what we're going to see next week, where some element of our reactor depends exponentially on temperature, and then weird things can happen, because one varies really fast and one varies really slow. Good questions. Any other questions? No? Okay, I'm going to stop this. We've got 20 minutes left.